So today we're talking about thin layer chromatography or TLC, and it mostly deals with polarity of compounds and molecules. So that's the big message of today's lab. So far this semester, we've looked at solubility with polarity, we've looked at functional groups, we've looked at some chemical tests that you can do. So now TLC kind of ties in a lot of those pieces because it's polarity, it's intermolecular forces, it's what else is it? Functional groups, and it's also another kind of lab test that we can do. Okay, so the purpose of TLC, we're comparing different polarities. We're determining how many components are in a mixture. So TLC can separate out different components that are in a mixture. And we can also monitor if a reaction is taking place or at what point the reaction's at. So a reaction is, if you remember, if you've taken inorganic recently, it's you start out with some reactants and then you either have a catalyst or you're combining some things, you're adding heat, something's happening where you end up with a product. So there's a phase change happening. So you go from reactants to products. So those are the three purposes of TLC, the thin layer chromatography. I just wanted to go over some applications in real life because sometimes it's like, well, I don't really care about TLC. What does it matter? So there's a lot of different fields that use TLC. So purity of a sample. Next week, when we do an aspirin lab, I'm going to be going into Simmons and synthesizing aspirin. So I was thinking of running a TLC of my aspirin product because that's a way that I can tell if my aspirin is actually aspirin or if it has some starting materials still in it, which would mean that it's impure. So you want a pure product. You don't want anything in it that was a starting material. You want it just to be aspirin, not aspirin with whatever else that you were using in the experiment. So purity of a sample. This is an example of examining the reaction of something. So you're going from A to B. You're starting with A and you end up with B. So you would take a TLC plate here and you have A, which is your reactant, and B, which is your product. And then you have a mixture of both of them. And that mixture is what you're going to monitor to see if it's undergoing a chemical reaction. So you would run 3 separate TLC plates. So this is the first one you would run, and you see that your product, or B, goes right to completion. It's all done. A is your starting material. It doesn't go very far. And then your mixture is still in the early stage of the reaction, so it also doesn't go very far. So you know that it's lining up with your reactant. Then you toss that TLC plate, you start another one a couple minutes later or a minute later, however much later you want to time it. And then you see that the reaction's progressing. So you see a little bit of product, but you also see that you still have reactant present in your mixture. So you know you're not completely in the clear. And then you do it a third time, and you can see that you have no reactant left, and you're just left with a product. So your mixture ended up undergoing its chemical reaction. So that's how you would examine a reaction with TLC. Biochemical analysis. I didn't really look into these. I want to say something about, I saw like a little article about doping. So like, you know how in Olympic sports, you have to get tested for metabolic steroids and stuff like that. I thought I saw something about using TLC for that to test body fluids of athletes for doping, but I'm not 100% sure. But it can also be used to test body fluids. So like blood, serum, plasma, things like that. The pharmaceutical industry, so again, impurities in drug products, if anyone's interested in pharmacology. So one study I found was identifying counterfeit drugs. So in this study, I linked it here if anyone's ever interested. So in that study, they looked at malaria drugs. I think they were doing the study in Malawi, and I think malaria drugs are pretty expensive. I don't know the cost, but I would assume that if they're being counterfeited or yeah. So they took malaria drugs from a pharmacy, and then they went to street vendors who were selling malaria drugs that they, put into different packaging. And they were testing to see if it was actually a malaria drug that they were getting from the street vendors. And they were able to use TLC to find out that I think it was maybe there was like Tylenol in it, something innocuous, nothing bad. It was like Tylenol or aspirin or something, and it wasn't actually the malaria drug. So that's another way to use TLC to identify counterfeit drugs. The food and cosmetic industry. So you can look at if there's preservatives, you can spot a preservative on a plate and you can run that plate and see if there's preservatives in your product. Pigments in lipstick at a crime scene. That was another like research article I saw. It wasn't too convincing though. I think there was a little bit of a gray area with that, but basically lipstick is made up of different pigments, oils, waxes, and fragrances. And if you find a lipstick at a crime scene, you can compare the pigment in that with, I guess, controls or other lipsticks. It's used in forensics, basically. And then another one I thought was interesting was in perfume. So I don't know if anyone here is sensitive to perfume, but it's pretty common that perfumes can cause some type of breathing problems or allergies in people, either rashes. If you work in healthcare, you probably know that perfume's a no-no when you go into work. So I remember being sick once and like smelling the perfume, and like it really does not make you feel well. So I found that phototoxins are the toxins that cause allergic reactions, and they can be found in perfume. So I couldn't really find much chemistry behind the perfume industry online, at least. But I was thinking that a possible use for TLC would be quality control testing. So a perfume person could take their perfume and expose it to light or heat, and before they release it to the public, they test it to see if there are phototoxins that are present in the perfume after it's been exposed to light or heat. Because before you release a product, you want to make sure that it's good quality and it's not going to be harmful to people. So those are some of the applications of TLC in the real world. Oh yeah, this was something else I found when I was looking at the perfume. So this is the ingredients for Chanel No. 5. And I was thinking of an experiment could be for this, like you're a perfumer and they're like professionals and they can literally smell any smell and identify it. That's like their trade. So like if you have a new batch of perfume and the perfumer says, well, I feel like there's not enough rose smell in this batch, like let's test it. You could spot a TLC plate with geraniol and spot, a batch from last year that smelled perfect, and you could see if geraniol is present in your new batch, the same as it was in the old batch. So these are different things that you can do with TLC because it's low cost, it's pretty effective, and you don't need a lot of equipment for it. So those are the applications. All right, so these are the terms that you're going to hear in the JoVe video. So stationary phase, so stationary, it's not moving, it's just standing still. That's going to be your TLC plate, or your TLC plate, because your TLC plate during TLC doesn't go anywhere, it just remains where it is. So we think of that as stationary, like a stationary bike. It's just sitting there, it's doing work, but it's not going anywhere. So your stationary phase is usually made up of a plate coated with silica gel or alumina. We mostly see silica. So silica gel looks like this. You may have gotten it in like I eat like seaweed packets, or if you buy like a leather product or like a leather wallet, you might see a silica packet in it. It says do not eat. So that's the same thing that these TLC plates are coated with. It's basically purified sand. So sand is made up of quartz and silica. So this is just purified sand without quartz in it, pretty much. And another name for it is silicon dioxide. So when you get this packet in food or leather products, it's because they want to reduce the humidity of the product, because this silica gel here water sticks to it, it adheres to it because it has all these hydroxyl groups on it. And if we remember that these are, they like water, they're highly polar. So that's the purpose of the silica. And then those are the plates that you'll see in the video. They look like this in the video. And it's basically a piece of glass that's coated with ground up silica. Okay, so that's the first term that's really important, is our stationary non-moving phase, and it's going to be highly polar. Our silica is highly polar. Another important term is the mobile phase. So mobile is moving, and there's some type of movement happening. That's your liquid phase. It's going to be a type of solvent that you're putting into your TLC setup that's going to get, that's going to start, it's going to move. Okay, it's not stationary. This is the mobile phase. So the solvents you typically use as your mobile phase are going to be non-polar. In today's activity, we're only talking about hexane as our mobile phase. And that's because hexane is non-polar. There's no in between. It's not slightly polar. It's not slightly non-polar. It's completely non-polar. So it's easier to use silica, which is highly polar, and hexane, which is non-polar, when we're talking about TLC. Next is solutes. So solutes, you're going to see in the video that that's what you're going to mix with some type of liquid, and you apply it to your TLC plate. You spot it onto your TLC plate. Development solvent is used interchangeably with mobile phase. So development solvent and mobile phase are basically the same thing. The development solvent is going to be the hexane, and it goes in the bottom of our TLC setup, and you'll see that in the video. And that's where you place your TLC plate into. So it works its magic, which you'll see later. Next is our developing chamber / container. Sometimes it's called development chamber, but developing chamber, container, it's where you're running TLC plates. And typically you use just a beaker, just a glass beaker, and a watch glass, which is a concave piece of glass that you put it over the top of the beaker. And you have to put a watch glass on because usually these solvents, these development solvents, are very volatile, and that means they're evaporating and producing vapor. So in order to stop them from evaporating, you have to have a closed system and put the watch glass over the top. Okay, next is our solvent front, and you'll see in the video the solvent front are once the TLC plate is placed into the development chamber or developing chamber, you'll see the development solvent start to creep up the TLC plate, and that's from it's called capillary action, but it's all those vapors that are in the chamber that are bringing the solvent up. So once you get to a certain height, not at the very top of the plate, but like just below the plate, you want to remove your TLC plate from the chamber, because you never want your solvent front to go all the way up and take over the whole surface. You want to make sure that you stop it there. So our solvent front is the height at which our mobile phase, aka our development solvent, climbs up our TLC plate. All right, and last is the origin. So origin is where you're spotting your solutes. So the starting line pretty much is called our origin. Okay, any questions so far? Because now I'm going to play the video. It's like seven minutes and 40 seconds. Okay. So I actually need to stop recording because I don't think I'm allowed to record this video. Yeah, so these were the steps that they took. So step one was the spotting the plate. So there's your TLC plate. You label it with what you're spotting onto it. You use something called a capillary tube. So it's this really, really tiny, it's almost like a straw for a hamster. It's just very small and thin. And you dip it into your solution, or your solute rather, and it just sucks up the liquid. It's like such a tiny space that I think it just carries it up. So then you would just spot it onto your TLC plate. Okay. You're preparing the chamber. So another thing that they did in the video, they put the filter paper on the bottom of the beaker, which I've never done before. I usually stand it up on the sides. So when you're preparing your chamber, these are the things you need. You need your beaker, the watch glass, so you can control the evaporation of your solvent, your development solvent. And then the filter paper acts as a wick. So the filter paper becomes wet, and because it's wet, it is giving off all of the vapor that maybe wouldn't reach, all the areas of your beaker. So think of the filter paper as a wick, and it's infusing your chamber with vapors. Okay, so that is the setup. And then in today, we're only talking about hexanes used as our solvent, which is non-polar. So that is the development chamber. And then when you're developing your TLC plate, you want to stand it up straight so the origin is facing down. And it's like they're going to be racing in an uphill battle, like they just travel up, up, up. And then you'll notice that the development solvent, so pretend that's our hexane, is nowhere near our origin line there. It's down below there. So you place the TLC plate in, and then the mobile phase starts to creep up here, up, up, up the plate. And once it reaches a centimeter from the top, or they use 5 to 10 milliliters. So yeah, is that a centimeter? No, I don't know. I'm bad with metric. So once it reaches, we'll say a centimeter from the top. So you'll see it in the beaker. And if it gets to that point, you pull it out with tweezers and you mark the spot with your pencil, and then you let it dry in the fume hood because it's probably a little bit volatile smelling. Visualizing it, so that's what they were showing in the video. So the UV lamp would look like that. So the spots aren't really visible unless you put it under the light. So with a nice sharpened pencil, you'll circle the spots or shade them in. If you use potassium permanganate, which is this pretty purple color, you just dip it in there, and again, you just circle the spots with your pencil. So that's visualizing it. This is the important part of TLC. It's the RF value. So here is the equation. It's the distance the spot travels over the distance that the solvent traveled. So up to that solvent front where you draw the line at the top, that's the distance the solvent traveled. So here's just an example. You'll do a couple calculations on the group activity, and then on the quiz, there's a question you're given. You're given these numbers here. You're given distance the spot travels, and you're also given distance the solvent travels, and then you have to tell me the RF. So let's look at A here. So here's A. A traveled, and we always want to use centimeters. That's another thing. So this is always in centimeters, but you don't have to show centimeters as a unit. It's just when you're measuring or when you're determining the distance, you want to use centimeters, but there's no units associated with RF. So we have A here, which went up just under 1. So we're going to say the distance that spot A traveled was 0.7. So we would write RF of A, or they wrote A and then RF, something like that, so you can tell which spot you're talking about. And then the solvent front is this line here, and it went up to about 4.7, like they wrote here. So the distance the solvent traveled is that solvent front line. So we're going to divide 0.7 by 4.7. So our RF of spot A is 0.15. And then we would do the same for B and C. M looks like it's a mixture of things, so I think they're only calculating A, B, C here, but B, so B went up to about 4.1. We know our solvent front is 4.7, so we would divide 4.1 by 4.7, and that gives us 0.87. Okay, any questions about that? Okay, I need to turn on the light here. It's very dark. Okay, that's better. All right, so that's your RF. Just quick question. Does anyone know, so if we develop this in hexane, which one of those spots, A, B, or C, do you think is going to be non-polar. So we're using silica plate and hexane as our solvent. Which one wanted to go to school?
B.
Yep, exactly. Yep. And then, yep, so B is traveling up, up, up. It's going with our nonpolar hexane because it's attracted to it. So we would guess that B is going to be our least polar or nonpolar. So they're used interchangeably. So the least polar, aka the nonpolar, is B. And then which of those spots, A or C, do you think is the most polar? Is staying in bed?
A.
A, yep, exactly. So A is very attracted to the silica plate because it's polar. So A doesn't want to go to school. It traveled the least distance. So that's another way that you can tell polarity. If you know that your solvent, you know the polarity of your solvent, and you know that you're using silica gel, which is polar. So you can look at simply the RF values and say, oh, A has a really small RF value compared to B. I know that A didn't travel as far. So I know that A must be polar and B must be less polar or non-polar. Awesome, good. Okay. I'm not going to go into this. I put this in here last minute last night, but this is like troubleshooting. It's not applicable to us. If you ever do TLC somewhere, maybe this would be helpful to you, but we can just skip over the troubleshooting here. Okay, now I'm going to do some polling questions here. All right, so polarity there in the group activity, you have to identify the London forces, dipole, dipole, and hydrogen bonding, because those also have to do with how your spots are going to behave on your TLC plate. So it's those intermolecular forces that cause the molecules to move which way or whatever, and which ones are going to adhere to our polar silica gel. So non-polar compounds are binding to our silica gel only with London forces. So that means that the London forces are incredibly weak. They're the weakest of all the forces. So if we're thinking, oh, the London forces are so weak, we would expect them not to really hold on too tightly to the silica. Anything with London forces is going to travel pretty quickly because it's easy to break those intermolecular forces because they're so weak. Then we have dipole-dipole forces. So those interact a little bit more strongly. They're kind of at the middle. They're not strong and not weak. They fall in the middle, but they're more strong than London. And then the strongest intermolecular forces, the ones that are going to adhere to the silica the most strongly, are polar compounds. So polar compounds that can ionically bond or can hydrogen bond to the silica are going to stay on the silica plate, and they're not going to travel up with our solvent. Because hydrogen bonds are the ones that are the strongest and they're the hardest to break. Okay, let's see if I can just skim through this. In general, yes, so the stationary phase, so your silica gel, which is the stationary phase, the part of your TLC that's standing still, is strongly polar, so it's binding to your polar substances. Anything here? Yep. So the moving liquid phase is usually less polar, aka it's non-polar, like our hexanes. So those are going to dissolve substances that are less polar or non-polar. All right, so this is going to be helpful in ranking. With your group, you're going to have to rank the strength of intermolecular based on the intermolecular forces and the functional groups of different molecules. They're like decanol, decane, different 10 carbon, and then there's one ester there. So I gave you all the info for carboxylic acids and esters because I know you haven't done carboxylic acids in lecture yet. So I identified those, and I also did the ester as well, which is butyl butyrate. So those answers are there. But this chart is showing you the most nonpolar functional groups, which are the alkanes. Alkenes is not included, but alkenes would go right here after alkanes. So alkanes, alkenes, and then you have your esters. So you're slowly getting more and more polar. You're going from nonpolar to polar. Then your aldehydes, there's a ketone on the worksheet. There's an alcohol. And then carboxylic acids are just before water in terms of polarity. They're super polar, highly polar. You'll be learning about those more with Professor Levy. So that'll be helpful when you're doing the group activity. And then I just gave you the types of intermolecular forces that are present in these functional groups. So carboxylic acids and alcohols participate in hydrogen bonding. Dipole-dipole are going to be the ketones, aldehydes, and the esters. Those all participate in dipole-dipole. And then London are hydrocarbons. So the weakest for intermolecular forces are going to be your carbon chain. So alkenes and alkanes, which is on the group activity as well. So all of this should be helpful with the charts that you fill out. And then that's it. So the group activity is 20 points, and then you submit one copy per group. I think the best way to do it is to create a Google document, and then one person or all of you can be typing, but you can designate one person to actually upload it to their Google Drive, and then they can share the document with all of you. So I only want each group's document in one person's Google Drive, so there's not multiple documents that I'm having to skim through. So one person uploads your document to their Google Drive, shares it with all the members, and then make sure to put everyone's name on the document as well. And then just to see, how you feel independently about this information, and if you've understood the TLC, there's just a 5-point quiz on 2U, so it's due at 11:59. And the questions on there are, you'll calculate like an RF, and you're given the distance that the spot traveled and the distance of the solvent front. So you would just do that division. And then based on the RF numbers, can you identify which one's more polar and which one's less polar? So remember, less polar means non-polar, and more polar means polar, pretty much. Okay.